All right. So let's start with graphs. So graphs, we know for sure it has a lot of applications. So we're going to look at it shortly. Ideal situation, the recommended textbook you are expected to use is still the reasonings book on discrete mathematics and its application, specifically the chapter 10 elaborates more on graphs. Now, one thing you need to know is that the last time we met, we started looking at some little aspects of data structures. And then we found out that data structures deals with the way we can manage and store data, right, in memory. So we realized that there are two main categories. We have the linear data structures and the nonlinear data structures. And for the linear data structures, that is where we can be able to have data sequentially. And one of the typical examples you can think of is the queue, right? We can also look at the stack, right? So a lot of them we can be thinking of. So for the queue, you know for sure that anytime you want to access data or elements, it has to be at the front of the queue, right? So element is inserted from behind the queue or at the real part of the queue and is served at the front. So that's why we deal with the first in, first out when dealing with the queue, right? And when it comes to the stack, like the way we have a stack of plates, I'm lying down somewhere in the kitchen, right? Ideal situation, once we have a plate placed at the top, right? That is the first plate that is expected to be picked. You cannot go and pick the last plate underneath, right? So we learned partially last week when we are dealing with trees that the stack deals with the last in, first out. That is the level. Okay. So today we're going to look at another type of nonlinear data structure, like the way we did for trees last week, because trees, we are made to know that it's a type of nonlinear data structure because the elements are assessed not sequentially, right? So the same applies to the graphs. So the graphs too, we're going to assess element non-sequentially. And we're going to look at the relationship between the tree and the graph shortly, right? But one thing you need to know is that for the graphs, we are actually dealing with the nodes, but the nodes in graphs, we refer to them as vertices. And then, of course, the connectors between the various nodes or vertices, we refer to it here as edges or arcs. So you have been made to know that a graph is a type of nonlinear data structure, and it is expected to be used for real-world applications, right? If you want to use the Google Map location, you need to be able to understand how the principles of graph algorithms work. So that if I'm standing here and I can be able to move from my internal location, which is called the source, to another location, which is going to be referred to as a destination. The graph theory, in terms of how the Google Map works, is able to model and give us the shortest possible path, which has less traffic congestion in that road. Okay. Again, the same way you're able to use your Bolt, your Uber, your Django, and all the kinds of things you can think of, right? They are all based on the graph theory, right? And it makes use of a particular algorithm referred to as a map matching algorithm. So because of that, you're able to stand at your source, and then you're able to now look at the app to tell you the active nodes which are close to your location. So it maps them to your end. And at the end, those who are interested can either accept your right offer or reject it, right? So that's another example of it. Another example too is like the way you deal with your Facebook, right? Sometimes you can be there and you can receive a lot of suggested friend requests, right? This is actually based on the graph. So the algorithm is able to look at your friends and also check the friends of your friends and recommend them to you as suggested friends. Again, it's able to also go extend to be able to also suggest you as an alternative friend to another friend of yours or another friend of yours. So at the end, there is this length of nodes whereby here, the users of Facebook are going to be active nodes, which can be recommended through friends to another friend. Okay, and that is how the graph theory works. Another thing you need to know is that when we talk of a graph, it is slightly different from a tree because a tree has one of the nodes which is dedicated as the root node. For graphs, we don't have any of the nodes dedicated as a root node. Of course, you can start with any of the nodes at all when you are doing the tree, the graph visitation. And as I mentioned earlier on, the set of nodes in trees, in graphs, we refer to them as vertices, and we also refer to the connectors as edges or arcs. Unlike the trees, graph will have no restriction with respect to the connections between the nodes. This means that nodes can be connected in any possible way at all, right? The relationship between a tree and a graph is that a tree can be treated as a special kind of graph, right? So as we move on, we look at that type of graph and we'll be able to understand that, okay? So we know that basically these vein 1, vein 2, vein 3, all the way to some vein 8 can be seen as the vertices. One is vertex, and then the connectors can be seen as the edges, which you can also refer to them as what they are. Okay. Then we know for sure that if I'm moving from vein 1 to say vein 2, I might have to call my vein 1 what the origin or the source, and I'll refer to my vein 2 as the destination. Okay. So that's something we really have to also understand. Now, anytime you see a graph modeled in this way without arrows, then we can refer to it as what? An undirected graph. Okay. Once there's an arrow or there are arrows, then it becomes a directed graph. Imagine there's an arrow from vein 2 to vein 1, right? Here. Then we cannot move from vein 1 to vein 2. We can only move from vein 2 to vein 1. That's what I'm saying. So imagine there is a particular arrow here. And of course, there's another arrow here. What it means is that the vein 2 here becomes the origin, and then the vein 1 here becomes the destination. So meaning that vein 2 can only move from itself to vein 1, but not the vice versa. Same way, vein 1 can move to vein 4, but vein 4 cannot move to vein 1. And that is how the directed graph works. For undirected, there are no arrows. Look at the example, vein 3 and vein 1. We can have vein 3 moving from that side to vein 1, or we can have vice versa. So at any point in time, vein 3 can be an origin or can be a destination. Likewise, vein 1 can also be origin or destination respectively. And one thing you need to know is that graph can also contain both directed and undirected graphs. There are instances we need to be able to put restrictions to be able to have one particular node moved from the origin to the source, and the other ones we don't need any issue on that. I've already mentioned what the edges. I've already mentioned what the vertices is, right? So some of the things I might skip them, right? So that we can be able to finish on time. So here we have a directed graph with the arrows which I've explained, and then the actual name is what you call the digraph. And an undirected graph which has no arrows pointing. So some of the applications I've already mentioned with regard to social network like Facebook can be modeled using undirected graph. Intercity roadmap can be modeled as undirected weighted graph. So the weight here can be the distance between the two cities, right? And that's something I really want you to also pay attention to. Am I hearing someone say I cannot hear anything? Please, can you hear me?
Yes, we can hear you, sir.
Okay, good. So the other properties of graphs, maybe this one's I'll skip for you to read. That has to do with a self loop, whereby if you move from your side, you get to your intended same location. You don't move away to another node. And the multi-edge to same, I'll skip that. Let's look at this. Self-loops and multi-edges make a graph complicated to work with. So a graph with no self-loop or multi-edges is what we refer to as a simple graph. So let's assume I have this particular graph, right? The number of edges is what we want to look for. So if you have the number of vertices in a simple graph, what would be the maximum possible number of edges? Once we know the vertices, our main task is to be able to look for the extreme case if all the vertices or the nodes are connected. What can be the maximum number of edges that graph can possess? Now, in this situation, one thing you need to know is that it depends. If this particular graph, right, V1, V2, V3, V4, right, which is modeled as a set of V to be equal to this possible number of vertices, then in general, to find that number of edges, right, then what we are going to say is that we're going to have the cardinality of the size of V to be equal to N, meaning that N is already known. We know the total number of vertices. And this total number of vertices in this case is 4. Can you see that? So if you are dealing with a directed graph, then the formula now becomes 0 less than or equal to cardinality of E less than or equal to N going into N minus 1. Please hold on, Steve. Your class will be So for the directed graph, we're going to have the cardinality or the size of E, where E will deal with the number or the total number of maximum edges we can have or arcs going into N minus 1. So we can easily compute that, right? So if N here in this graph is 4, it's going to give me 4, right, times 4 minus 1. And that's going to give us the E and this is for directed graph, right? Less than or equal to what is here. So at the end, this one is going to give us less than or equal to 4 times 3. So this one give us 12. And this 12 here, because it's E is less than or equal to 12, we can now say that the maximum number of edges this particular graph will have is going to be what? 12. And I don't know whether you can see that. So if you check, because it is directed graph, you can easily do the counting, right? Directed means that it is actually going to go in all directions. So I'm going to have 1, 2, 3, 5, 6. Then we can repeat for the others, right? So we can also have another one here to be 7, 8, 9, 10, and then we can now come here 11, 12. Can you see that? So at the end, we can have a maximum number of graphs, edges to be 12 if you are dealing with a directed graph. Why? Because this one is 2. One side here, V1 to V2. The same thing again, you can have V2 to V1. Now, if it is undirected graph, then at this situation, the whole of this top is what we had maximum of 12. So to have it for undirected means that we are not going to have these two arrows. We're going to have a single arrow, where at any point in time, one can serve as the origin, the other one can serve as the destination. So if that is the case, we just have to divide this 12 by 2. And that's going to give us 6. Why? Because the whole of the top here, n going to n minus 1, is what we had at the 12. And then we can divide it by 2, that gives us 6. So at the end, this gives us 6. Now, if it's 6, let's count and see. So I'm going to have 1, 2, 3, 4, 5, 6. Any question? Please, can you hear me?
Yes, sir.
Yes,
So
sir. We can hear you. Hello.
Okay.
We can hear you.
Yes. Let's move on. Now, some properties of graphs, maybe this one you can actually look at, right? A graph is called dense graph if the number of edges is, it is close to the maximum number of edges. A graph is also called sparse graph if the number of edges in it is close to the number of vertices. Okay. So these are some of the things that we need to be able to know. So at the end, we can be able to have the adjacency matrix and the adjacency list. So for adjacency matrix, it's going to look at the fact that it is a dense graph, whereby for dense graph, all we are saying is that we have too many edges. And then for the other phase, which deals with the adjacency list, we're going to have few edges as well. Let's look at a path. A path in a graph is a sequence of vertices where each adjacent pair is connected by an edge. So when you talk of an adjacent pair, all that we are saying is that two edges share the same connector. Two vertices share the same connector. So vertex A, vertex B, they are sharing the same connector. So we can call A and B adjacent. We can also call that A and D now adjacent to each other. A and C same. But A is adjacent to J because there's no straight connector. Now, in an undirected graph shown, A, B, F, H is a path. A path between two vertices A and B is called the AB path. Now, in a case whereby the vertices are not repeated, right, we call that particular path a simple path, right? So for example, I can have A, B, F, G, A, B, F, H, A, B, F, H. And that's a typical example of a simple path. Now let's look at the walk. Can you mute yourself, please? A walk is used to denote path in general. And the term path indicates a simple path. Okay. So that's what a walk is. Thus, a walk in which no vertices are repeated is called a path. The case whereby the vertices are repeated is what we call the trial. So at the end, I can be able to call A, B, F, A, B, F, H. Where is it? A, B, F, sorry, H. Then we go to E. Then I come to pick B, which has already been written. Then I go back to A. And I come to D. So realize that in this case, vertices B, A, D have been repeated. And when we have such a scenario, we can now call it a trial. For the strongly connected, weakly connected strong, these ones are things I think you can read on your own. So I'll skip that. Now let's come to a work is said to be closed. So this is an undirected acyclic graph. And if you see very well, you have no other option than to say that that is why we said that the tree is a type of graph. Why? Because it is a type of acyclic graph, right? Specifically a non-directed acyclic graph. Then you can have the directed acyclic graph as follows. These are all examples of acyclic graphs. For the edges, these are easy. Before that, I hope I made you aware that the graph can be mathematically defined as J equals to V comma E, right? So the edge, we can be able to have the connections between the two of them, and that's good to go. Skip this. Let's skip this. Let's skip this because you'll be getting more details of this when you are doing second year at data structures and algorithms, right? And one possible of representing graph is by using a two-dimensional array or matrix for storing the edges or the edges. So we can have the vertex list A, B, all the way to H. Then we want to be able to have this particular 2x2 matrix in terms of rows and the columns. So what we are going to do is that this A is going to be modeled as 0, this B is going to be modeled as 1, this C 2, all the way to the last value here. Okay. Then what we're going to do is that for you to be able to get this, all we need to do is get adjacent matrix. You need to be able to look at the fact that was A having any self loop. If it's not having any self loop, then we're going to have AA 0. Then we come to AB. From A to B. You realize that from A to B, there is a connection. Once there's a connection there, we're going to indicate with a 1. If there's no connection, we indicate with a 0. Then we're going to have A to C, right? So let me help you. This guy will be A, right? This guy will be B. This guy will be C. This guy will be D. This guy will be E. This guy will be F. Of course, this guy will be what? J. E, F, G, H. Okay. So the same logic here. A, B, C, D, E, F, G, H. So if I'm dealing with A alone here, I'm going to leave the rest. I'm going to only deal with A. So I'm going to have A 0. A, B, is there any connection? Yes. So we're going to indicate a 1 there. A, C, is there any connection? Yes, so there's a connection that will be indicated with a 1. And then AD, yes, there's a connection that will be indicated with a 1 here. And then AE, is there any AE? No, there's no connection. Okay, so once there's no connection between A and E, that will be 0. The same applies to A and F. The same applies to A and G. And then lastly, A and H. Okay, so because A and H, there's no connection, we're going to put 0 there. And we do the same thing to complete the whole table. Okay, any question on this?
Hello, sir.
Yes.
Please, are we pairing the numbers or the letters on the vertical axis to the horizontal or the horizontal to the this vertical?
Any will hold.
Any will hold.
Yes.
You
Any
can
row.
choose any of them to use.
Yes, if you want to do A to B, A to A to B, it's the same thing. If you like, check. This is 0, 1, 1, 1. See,
Okay.
0, 1, 1. Then 4 zeros. Let's see, 4 zeros.
All I'm saying is that so assuming I'm using the vertical one to pair with the horizontal.
You get the same answer.
And so when I use A to pair throughout, then I come and use B to start with the A on the.
Yes.
All right. So any
still-
of them you choose, you still get the same answer.
I get a pair horizontal, this row wise
Yes.
or the horizontal, and
Okay,
I
that's the
connect
one.
each of the vertical values.
Okay.
Whatever answer I'm going to get is going to be the same guy who's also dealing with vertical, pairing
Okay.
with the horizontal ones, right?
Okay. Sir. Thank you.
No further question.
Hello, sir.
Yes.
Before you do this, would they give you the graph so that you use the graph to show the table, the matrix?
No, you expected to know that already, right? As when the person asks you to construct the graph, you should be able to do that. Okay.
So you construct the graph and use the graph to fill the table.
No, the graph will be given to you, but you have to
And
construct
they will
the
give you the graph so that you plot this thing. They will give you the table, then you plot the graph, right?
okay. So this one to any can hold. You can be given the table,
Mm,
can be used to plot the graph,
okay.
or you can be given a graph and they ask you to construct the matrix.
Okay.
Please, yeah.
Yes, please.
Okay, we
Thank
move
you.
on. You're welcome. Undirected, the adjacency metric will be symmetric, meaning that at the end, whatever happens here will be the same thing that will happen here.
Hello, sir.
Yes.
Yeah, back to this one. You see, looking at the concept of the adjacent edges, we know they have a link together, right?
Yeah.
They are kind of connected. So looking at A, B, and F, okay, they are connected, right?
Yes.
But why is it that we cannot say A has a connection with F, but yet we are putting 0 at that place, or it has to move directly from A to F?
Yes. If it was like this, then we can say that they are adjacent.
But A, B, and F are also adjacent, right?
Yes. A is adjacent to B and B is adjacent to F, but A is not adjacent to F unless the line I've drawn holds.
Oh, so, okay.
Do you understand?
Okay. So with the same idea, if there was a line between D and G, they would be adjacent.
D and G, yes, they will be adjacent. Yes. If there was a line, they would have been adjacent.
All right.
Okay, so we move on right quickly. Today's holiday, I want to take much. Did you have any class apart from my class? Did you guys have a class today?
Yes, please. Yes, please. We have started 111.
Okay, good. So we move on. So here, if it is a director graph, then we need to watch it. If you're moving from A, you go to B, it will not be the same as B to A. Because this one, you are being told that the starting node here will be A to B, A to C, A to D, and so forth. But you cannot move from B to A, neither can you move from D to, neither can you move from C to A. So if I'm checking B to A, let's see something. This is A, B, C. A, B, C. So B to A. So let's assume this is my B, right? And I want to get A. B to A is 0 because there's no connection. Likewise, if I want to also pick it from here. So this is B. Remember, this is A, right? The second part is B. Oh, sorry. And this guy is A. So if I'm looking at B to A, This is the way there's no connection. Likewise, if I'm looking at C to A, so here too no connection, all the way to the end, then you're exhausted. Okay. So I'll skip this once. I'll skip this. I'll skip this. Now there are instances whereby there will be some durations or the weight on top of the edges or the axis. So in that case, instead of indicating a 1 or a 0, we can just use the weight to be able to do the indication, and then we are good to go. Okay. I'll skip this. This is still more of the data structures. So I'll skip this. Adjacency list, doubly linked list, singly linked list. You learn it more when you're dealing with data structures. So for graph, we can have some kind of operations like the adjacent, the add vertex, remove vertex, add edge. You still get more details of that when you are actually doing data structure. So I'll skip that. I need to be able to cover some pattern and then. Now, there are instances whereby we need to be able to visit the various vertices in a particular graph. So we need to be able to know how we can use an algorithm to do that kind of graph visitation or graph traversal. There are two main ways to traverse a graph. The first one is what we refer to as the breadth first traversal or visit. And the last one is what we refer to as the depth first traversal or the visit. So let's start with the BFS, okay? Now, for the BFS, if you want to be able to visit a particular graph, the various nodes, assume you are given the starting node. The main idea here is to be able to look for the adjacent nodes to the starting node. And then visit all the adjacent nodes before you can move on to another adjacent node. So if you can see here, we have a starting vertex V, and then it is marked as visited, provided it's actually visited. If not, that particular unvisited vertices are placed in a queue. And remember we mentioned that for the queue, it deals with what we refer to as a first in, first out. Okay, so once a particular unvisited node, which is adjacent to the given starting node, is placed in the queue, remember, it will be the first to be attended to. So let's look at this one. So here, we have this particular pseudocode whereby you're going to enqueue a given unvisited vertex V to the queue cap kill, sorry. And then when it is visited and it's set to true, we can now be able to come back and check the queue. Is a queue empty or contains some elements? And you can see the indentation. Once the indentation is here, it means that we are going to now remove the first element in the queue and attend to it. And we call that one the queue. Now, once we dequeue, the next thing you're going to do is that if that particular U has been visited, you also have some adjacent nodes or friends. So what are you going to do for all vertices W adjacent, for all vertices W adjacent from U, if W is not visited, in other words, if W visited is false, we are going to enqueue W at the back of the queue, which is going to be the next to visit, until that particular W is serviced or removed at the front of the queue and visited. And remember, when it's about to get visited, we have to check if it has other adjacent nodes, so you place at the back of the queue. Maybe an example work.
Hello, sir.
So let's see this example
Yeah.
and see whether it makes sense. Yes.
Please take the explanation again.
So maybe the example will work for you, right? So please pay attention with the example and that will work for you. Now, we have a particular vertex A, right? Which is going to be the starting vertex. So that's what we are assuming. So no one come and ask me, why didn't you choose C as a starting node? So it is here. Can you see that? We assume that vertex A is a starting node. So meaning that at any point in time, you always be made aware of the starting node or the starting vertex. Maybe when you are done, you want to try a hand, C is a starting vertex, that's fine. So if A is a starting vertex, then at this situation, remember, all vertices which are adjacent to A has to be placed at the back of the queue. So what do I do? A is adjacent to B and also adjacent to S. So once I have A, I'm going to have B, I'm going to have S as number 2. And these guys are going to be placed at the end of the queue. So B goes first, followed by S. The reason is we saw it in the alphabetical order. If there were numbers, if there were names, you're going to deal with alphabetical sorting. Okay. So if there are numbers too, you're going to start with the least number before you go to the biggest number. So B goes in the queue, followed by S. And of course, A is visited. So we have A out. So that's why we have A out. Now, once we do that, we need to now come to the front of the queue. For queuing, there's something referred to as NQ and DQ. NQ has to be given an element to be inserted at the back or the rear of the queue. DQ doesn't need to be told which element to remove. All that the queue knows is that once that method the queue is called, it has to check the front of the queue and remove whatever element which is there, the first element. So if I'm going to call the queue, right, it is going to pick B. So if it picks B, right, B will now be taken off the queue. In other words, we assume that it has been visited. So if it has been visited, then what do we have to do? We need to output B as visited. And once you're outputting B as visited, we need to check whether B has any other adjacent node. In this case, B has no other adjacent node. The only adjacent node B had was A. And A is already visited. So we don't need to worry ourselves with A again. And if you check, B has no other node again. So when B is output, we don't add any other adjacent node to it, to the queue. Now, when we are done, remember S was marked as number 2, which is the next in the queue to be visited. So what am I going to do? All I'm going to do is that I'm going to also visit S. Visiting S means that I'm going to remove S from the queue, and I'm going to output S. But watch it, before I can output S, I need to also check who S is adjacent to. And S is, of course, adjacent to A, but A is already visited, so I don't waste my time with A. And S is adjacent to C and J. In terms of alphabetical order, C comes first. J now becomes number 4. Okay. So we can now put C, because of space, I'll put it here. And then put J. Okay. And we've already output S. So the next thing we need to do is to check what is next in the queue, and that is C. So for us to be able to visit C, we need to be able to know that all adjacent nodes to C has to be placed at the end of the queue. So if I'm going to output C, okay, I need to be able to know who is adjacent to C, and that is D, E, F. So D in terms of alphabetical order becomes 5. E becomes 6. F becomes 7. Now, if we are done with C, and when we come to the Q, we are going to be adding D, E, still because of space, that's why I'm writing small, okay? And then F. And these are already inside the Q. So if you check, because C is gone, we are left with J. Now, in terms of J, I'm going to add to J. And J is adjacent to F. F is already in the queue, so I don't waste my time. S is already visited, so we don't also waste time there. But J is adjacent to H. So I'm going to add H at the end of the queue. So this one becomes what? 8. And of course, J has to go away. Before that, hold on. So where are we? We are able to output. I'm sorry, let's go back. We have been able to output C. And when we outputted C, we need to come to J. Why? Because J is the fourth one. You know that? So if you output J, which is out, we need to now cross it out and place what is adjacent to J again to the back of the queue. If you are done with J, we need to now go ahead to look at the next one. The next one we need to look at is the one which is the next adjacent friend of C. And that is what D. So at D case 2, we are going to output D because we have visited D already. And once we are done with that, D has to be outputted, which is done here. But before we output D, we need to check whether D has any adjacent node. It's only C, and C is already visited. So we need to put C back again in the queue. Then we can now move on and check the next adjacent friend of the C, which is E, right? And this is E. So we're going to output E. Now, in outputting E, we also have to check whether E has any other friend, okay? And of course, E's friend, in fact, has already been outputted, which is what? C. And then now H is already added to the end of the queue. So E is gone off. Then we come to F. Of course, F also has this that can be deleted or to be visited. So we're going to output F. And of course, F has no other adjacent node because the C and the are already visited. So lastly, we come to the last node added, which is H. We're going to output H. And we are good to go. Any question? Any question?
Hello, sir.
Yes.
If you are saying that in terms of alphabetical order, why is that when we go to C, we do not move to D before coming to G?
When you go to C,
Yes. So you see, we have A is having this in B and S.
yes.
So B was 1 and S was 2. And we move to 3.
Yes.
C has 3.
Yes. C and then J, because they are the two friends of S. So
Oh,
that's why
okay.
we have 3 and 4.
Okay.
Then we
So I have
think
a question.
C. C has 5, 6, and 7. These are the,
As a friend.
yes, that's a friend of C.
Okay.
And then J, at this situation, also is having H, and then F.
F as a
But F
friend.
is already added to
A
the
friend
node.
to C.
Yes, so F is already marked,
Okay.
and that's already come here. Please, you understand?
Yes, sir.
Yes, sir.
Sir,
Okay. Yeah.
please, I want to know if the question can come this way. Assume vertex E is traversed first. Determine the output based on BFS.
Yes, you can do that. You
Meaning
can.
we'll start from E.
You start with E. Very good.
They can mention any letter at all.
Yes, any letter at all can be mentioned.
Okay.
So in your case, you start with E, right? So E will be the one to be outputted first. Then we need to check E is adjacent to what?
The
E
friends
friend is C, and then
C
H.
and H. Okay.
So C becomes 1. H
H
becomes,
becomes 2.
so I'm going to output C.
Okay.
Now, whilst I'm outputting C, I have to also check the friends of C.
Okay.
So the friends of C, so this one, this is gone across like this. The friends of C will be D, will be F, will be S. So that is also going to be 3. F is 4. And then S is 5. And of course, C goes out. Then I need to now come back to look at the next friend of E, which is H. And then before H can go out, I need to check whether H is adjacent to anyone. Of course, H is adjacent to Jane. Now, Jane here will now be number 6. And now I can now output H. Now, when I'm done with H, I need to now go ahead to now look for the next one, which is in the queue. Remember, I've not drawn any queue here. I'm using the numbers to deal with it. So if I'm done, I have to now come to the friend of E, which is D in terms of a vertical order. So I'm going to output D, but I need to check whether D is adjacent to anyone. Of course, the one D is adjacent to is C.
Already cancelled.
So it's already cancelled. So I'm going to have my D here. Then, of course, I need to now come to the next adjacent friend of C,
F.
which is F. And I want to check whether F has any adjacent node. Of course, it is this, which is already cancelled. So I don't have any issue with it. So I'm going to have F straight because F adjacent friends are all marked. Then after F, I can now come back to S because S is also adjacent to C.
C.
So when I'm picking S and I'm going to output S, I need to make sure that S is adjacent to who and who. S is adjacent to J
And A.
and A, but J is already marked. So I need to come to A and mark A as 7. Of course, I have to output S. So this is this. Let me just come down. Okay, so I'm going to go back again to S. All right, now when I'm done with S, I come back to the queue and I check what else is in the queue. And to know what else is in the queue, I know for sure that it's going to be J. So for J, I have to check whether J is adjacent to anyone, and all of J is adjacent to are all out. So I'm just going to cross J out, and I'm going to have J here. Now remember, I still have notes in the queue, which is what? A.
A.
And A is adjacent to S and B. Because S is already marked, I'm going to go straight to B. And of course, I'm going to have A here. And then A is adjacent to what? B. Oh, sorry, that is B. I'm sorry. There we are done. So that's going to be the output if you are dealing with E starting as a starting. The rest you can be able to do for all the other nodes. And then you're good to go. Any further question before we move on to the DFS? Any question? If you have any question, I think we can move on to the first, to the other one, right?
Yeah.
Yes, please go ahead.
The time complexity. That one is for what?
Non-complexity deals with data structures and algorithm. So when we talk of time complexity, we want to look at how long it will take for an algorithm to complete an assigned task. Okay. The most case scenario, we have three main categories. We have what you call the best case scenario. We have what you call the worst case scenario. And we have the average case scenario. Now, in this
Okay, sir.
situation, we are only interested most of the time in the worst case scenario. If you're able to find the worst case time complexity or space complexity of any algorithm, then we know for sure that the algorithm can be reliable. But if we can only find the best case and the average case, and then the worst case, the algorithm keep on running, it doesn't stop executing the tasks, then we are heading to a catastrophe. All right. So these things, you come across them more when you're actually dealing with data structures. Okay.
Okay, sir.
All right. But I'm not going to examine you on that. We can move on. Okay, so let's move on to the DFS. Now, the DFS is interesting because it works like how the BFS is. At this time around, the DFS has this nice approach whereby it's a little bit greedy, because if I'm visiting the nodes and I start with the first node, okay, who is adjacent to a node that's already been visited, I need to look for all the friends of that node I am on. I'll give you an example. Assuming like A is a friend to B and then S. Okay. And then this situation, I am at A, I visited A already, I go to B. Before I can finish visiting B, I need to make sure that I have visited all the friends of B and I'm done with all the friends of B. Before I can even think of coming to visit the second friend of A, which is S.
Hey.
And then come and visit all the friends of S as well. So that's how it works, okay? And it does what we call a stack, whereby here we can implement the last in, first out. So in this case, we have a simple algorithm here, whereby if the visit is true, then all we are going to do is for each vertex W adjacent from him, because that W has not been visited, in other words, it's false, we are going to repeat the whole DFS algorithm again. This time around, we are going to replace this bin, which is a parameter, with a W. And then come and say that if we have visited W, which is true, we can now look for all each adjacent node to the W, right, to that vertex, which have already been visited. We also take our time to explore it. So until we finish exploration, we cannot move on to another node. Now, there's another one here again. So here, anytime you want to be able to deal with the DFS, you want to push, right? Push means that you have a particular parameter V and you're pushing it to a stack S. In this case, if V is visited and is true, and then S, which is the stack, is not empty, we need to be able to attend to what is on top of the stack, and that's where we use the word top. That particular top is expected to tell us the element which is on above or on top of that particular stack. And once we have that, we are good to go. So if visitor W, then we can now pop S. Pop S means that you move whatever element which is at the top. In this case, we are going to pop what? That particular vertex. Now, once we pop it, for all neighbors, W of U, so what we are popping was the vertex U. And once the U has to go away, we need to be able to check all the neighbors of U. We are calling them W. Now, if a particular neighbor is not visited, in other words, if visited W is equal to false, then we are going to push that particular vertex on top of the stack. And because the stack deals with last in, first out, whatever we are going to put at the top of the stack will be the first to remove. So once we have it, then the W will be visited. And then we are good to go. Maybe let's take an example and see how that works, right? So the same example, the same preamble we're using. Let's see how we're going to be able to address that scenario shortly. And then see. So with the same thing, we're going to have a particular graph. This time around, we're still going to use the starting point as A. And if you're going to use the starting point as A, we need to know that that particular node, because can you hear me?
Yes, please.
Yes, we can hear
Yes.
you.
Okay. Because B and S are adjacent to A, right? We need to be able to start with that particular first node. And that first vertex in this case would be B, right? So if A is visited, right? Oh, let me change the color. If A is visited, A is out. So we're out with A. Now I need to be able to check the first adjacent node to A. This is where the difference comes in. And the first adjacent node to A is B. So I'll mark it as 1. Remember, I don't come and mark S. So when I put B into the stack, I am going to pop it because it's going to be the next to visit. So in the next to visit, B will be popped out. And once I visit B, I have to check whether B also has any other adjacent node. Unfortunately for us, B has no adjacent node. So I have to come to S. Why? Because S is the second friend of A. And I came to S because B is not connected to any other node. So I'm done with B. Now, when I come to S, which is going to be marked as 2, before I can visit S, I have to check who is the next immediate friend of S. That particular guy is what? Is C. So S is visited. And outputted. Then I go to C. And I have to visit C because that is the next immediate adjacent node, which is marked as 3. Once I put it at the stack top, I have to visit it. So when I'm at C, I visit, watch this. Now this is where the difference comes in. And then C is output. Then I need to also check that particular adjacent node to C. In this case, is D. So I mark D as the 4th. Now, when I'm at D, I have to also pop D and check whether D has any other friend. Of course, D has no other friend again. So D is output. Then I can now come back one more and come and check the next friend of C. Remember, not S again. I have to completely exhaust every possible friend of C before I come back down. So when I'm at C, I realize that, hey, C has a friend called E. So I go to C, whose friend is E, right? And I mark it as 5. Then I visit E. E is out. Before I can be able to do anything, I have to also check the next adjacent friend of E, which down here is H, 6. Can you see that? Then I visit H, because H is on top of the, sorry. H is on top of the stack. So I visit H. Now, when I'm done with H, I have to output H. And as I'm outputting H, I have to also check whether H has any other immediate friend or adjacent friend. And if I check, it's Jane. So Jane is also marked as what? 7. Then I visit Jane and output Jane and check the next adjacent node to Jane, which is F. So I visit F. And I check whether F also has any adjacent node. It's C, but C is already marked. So whatever I do, I realize I finish. And if you check, when I was at C, I never came to Jane. It actually led me until I realized that, hey, Jane is also a friend to H when I was at H. Then I'm done. And that's how the depth first search works. Any question?
Oh.
Hello?
Yes, any question?
Yeah, please, what you just said that when you got to S and you moved to C, why didn't you move to G?
When I was at S,
Yeah,
right?
the immediate adjacent, you moved to C.
Yes, I moved to C. Good.
But then what about G? Can't it be an immediate adjacent? Or it wouldn't work?
If you are looking at Jane, C and Jane, then you're looking at breadth first search. So that's why I didn't come to Jane.
Okay,
Jane
okay.
is also an adjacent node to S, but remember I began by saying that we have to look at alphabetical order.
Yeah. Okay,
All right.
that's
Any
fine.
further question? If you
Yes,
understand this,
sir.
try this.
Please.
I should go back.
So I want to, yes. I want to know if it's always going to be alphabets that will be given.
No, sometimes they'll be giving numbers, sometimes they'll be giving names.
Okay, so in any case that a name or names have been provided, how are we going to do it? Since we have to go by the alphabetical order of the items.
Every name will have a letter beginning with it. So even if you
Okay.
have Amma and Abigail, of course, they are all AA, but you and I know that Abigail will come before Amma when you are
Yes.
sorted. Great. So no matter what it entails, you definitely will have it sorted out.
Okay. Thank
Makes
you.
sense? You're welcome. All right, with that, let's try our hands on this. Let's try and see how we can get the DFS and BFS using A as a starting node. So each and every one of you, please try your hands on this. Find the BFS, DFS of this graph traversal and output the results. 3 minutes, let's say 3 to 4 minutes. Please, who is done? Hello?
Hello.
Has anyone finished? You have 2 more minutes, then we do it together, right?
Sir. Sir,
Yes, please go ahead.
please, the BFS.
You are
I
done, right?
got,
Oh, no,
yeah,
please hold on. Let your
okay,
other colleagues also finish. They will
Okay.
discuss. Okay.
okay.
All right. So let's do it. How many of you are done? Show by hand. All right. So I got someone who was trying to make the input of what he had. Let me write his input down. So the one who was speaking, what did you get
Yeah,
for the
it was BFS. I got B, D.
Please hold on.
Okay.
You had B.
Yeah, D,
Okay.
G, E,
Okay.
F, C, H.
Let's look at DFS.
For the DFS, I got confused.
Confused. Okay, that's fine.
Yes.
So let me get someone who can help with the DFS.
Yeah.
Then we'll solve it together. Yeah, please go ahead.
Yeah.
Right.
Please, the DFA, BE,
The DFS you had what?
BE,
A or B? We'll take our time. The DFS, what did you get?
BE,
B for boy. B what? E for elephant.
E for boy, E,
Okay, and then
G,
A, right?
G.
Getting him. B, E what? Anyway, let's do it together, right? So that at least we'll be able to get understanding well. But anyway, the answer for the BFS is wrong, okay? But that was a good attempt. It is wrong. I've not solved it, but I realized I didn't even include A
Hello, sir.
output. Yes.
Yeah, I want to give my DFS. I don't know.
Okay. Let me see yours.
Yeah, so my DFS was A, B,
A first, right?
yeah,
Okay, go ahead.
A, B, F,
ABF. Let me clean it. Let me clean. ABF, right?
yeah, F,
Okay, please go ahead.
C, D, H,
Okay.
and G, E.
GE.
Hello,
Yeah,
sir.
Yes.
Hello, sir.
Yes.
Hello, sir.
I can hear you.
Let me try. Let me give mine. The DFS.
Hmm. All right. Go ahead.
DFS is AB,
Mhm.
EG, FC, HD.
Okay, so for these two, I don't know the answer because we have to do it together.
Okay.
The first one, I realized that the answer would be wrong because the person didn't start with A, and A was a starting point, so A has to be the output. So let's do that. Let's do that together. If you also have your answer, you can also put it on the chat page, right? Okay. So we're going to do it together. So when we start with A, I'm going to have, and let me use a different color, probably move. I'm going to have the output to be A, which is going to be the first one. And once I'm outputting A, I need to also make sure that I have the adjacent nodes of A. In this case, I'm going to have B, which is the first, followed by D, followed by G. Okay, so we're good. Then at the end, because we're actually dealing with BFS, sorry, I need to now go to the next one, which is A, and then output A. Output B, I'm sorry. Output B. So when I'm outputting B, I need to make sure that I have the nodes of B, which are adjacent to that B, placed at the end of the queue. In this case, I'm going to have E and F. So this is going to be 4. And this is going to be 5. So what do we have? Since we have 4 and 5, all I need to do is I need to go back to the queue and then dequeue the next element, in that case, which is D. So I'm going to dequeue D. And then whilst I'm dequeuing D, I need to check whether D is also adjacent to any other node, which has never been marked here. And of course, F is there. So I have to now move away from D and come to the next friend of A, which is J. Now, when I'm at J, I'm going to add with J. And I have to check the next node, adjacent node of J. In this case, is E, and E is already marked and placed in the queue, so I don't need to worry my head. Okay. So I come to the queue and I dequeue. When I dequeue, E comes again, which I'm going to have E as a next node to visit. So I'm going to output E. And E is free to go because the adjacent nodes of E are already traversed or visited. So the next thing I need to do is now come to the friend of B, which actually gave me E and then F. So since F is the next in the queue, I'm going to output F. And I have to make sure that I get the adjacent nodes of F. And basically that is C. Now, once I am at a C, I can also output a C. And then of course, C's adjacent friend should be 1. That's going to be 7.
There we go.
So that's going to give me H. I think the first person had it with the exception of not adding.
Yes, I didn't know I was supposed to add A.
Okay, but now you know, right?
Yes, now I know. Thank you very much.
You're welcome. Great. So let's move on to the DFS and also compare the answers and see. So now let me use a different color. Probably let me use green. So I'm going to have D. Okay, so we come to DFS. Now, of course, here too, you don't need a switch here to let you know that A will be the starting node. Now, once I have A and I'm dealing with DFS, DFS tells me I need to first pick the first friend of A and then completely exhaust everything in that first friend. And that first friend here will be 1, will be B. Now, in outputting B, I need to make sure that I have all the nodes of B taken care of. So this one, of course, I have to close. So here too, I have to close the B. Now, what will be the first adjacent friend of B? In this case, it is not F, but rather E. So I come to E, and I mark E as number 2. And then E is out. Now, still at E, I need to check the adjacent node of E. That's J. And I mark it guy as 3. Now, when I'm done with J, I have to also check whether J has any adjacent node. And of course, the adjacent node of J is A, and A is already marked. So I need to move back, move back, move back. And then still at B, check the next adjacent node, which in this case is F. So I need to completely exhaust B before I can come to the next friend of A. So now I pick this guy, F, as number 4. So F will be the next to output. And then I cross F out. And what is the adjacent friend or node or vertex of F? In this case, we have C, we have D. In terms of alphabetical order, they're going to have C. So C here is going to be number 5. Now, when I'm at C, I need to also check the next adjacent node of C, where is H. So this will be number 6. Okay, then this goes up, this goes up. Then about F, I can see that the next adjacent friend of F is D. and I'm done. So let's see whether the person who had it is correct. A, B, F. No, this is wrong. A, B, E, J, F, C. Yeah, so this is correct.
Yes.
Hmm.
That is correct.
Happy the way you are happy is correct. All right, so that's good. Okay. If there's no question, let's try our hands again on this one. Oh, sorry. Sorry. Try our hands on this. This one to the starting node is A. You have 2 minutes. Okay. Maybe because of time, let's quickly do it together, right? Because your time is, I know you have another class at 3 o'clock. So quickly for BFS, let's see how it's going to go because we are dealing with the starting node as A. We're going to have it in a nice way. So we're going to start with A, which you're going to output. Then from A, you know that A has adjacent nodes. B, D, E. So this is going to be 1. This is going to be 2. Of course, this is going to be 3. So I'm going to go to B and I'm going to output B. And then outputting B, I need to pick the nodes, adjacent nodes of B at the back of the queue. In this case, I'm actually going to deal with C, C to be number 4. And then I'm actually going to go to the next one, which is F. That's going to be number 5. And I'm going to go to J, which is number 6. So these all guys are in the queue, right? So I'm going to have B. Then from B, I can now go ahead to deal with D in terms of BFS. So I'm going to go to D. Then from D, I go to E. Then when I'm done with that, I have to now come to the first friend of B, which is C. Then from there, I can go to F. And I can go to J. So we're going to have F and J. And then J. Okay. Now let's look at the DFS. Of course, that one I'm going to start with A because A is a starting node. Now when I'm at A, I need to go to the first adjacent node, which is B. So this guy becomes 1. At B, I need to also go to look for the next adjacent node of B, which is C. So this guy is going to go away because this guy is gone. This guy will go. Now, when I'm at C, I check what adjacent node of C exists. No one. So I cannot come to the next adjacent node of B, which in this case is F. So F now becomes number 3.
G.
And then of course, I'm not very sure I have to come to the next friend of B, which is G.
G, E.
Then I cannot come to D. Then I'll go to the last guy, which is A. And I'm done. Okay. The same applies to this. So in terms of BFS, so because of time, I'll just quickly finish it up. And here to starting node is A. So this is an example of a tree, an acyclic graph. I'm going to have this gone. I'm going to have A. Then when I'm done, I need to come to B to be 1, C to be 2. So B here will be gone. And then B is adjusted to D and E. Okay. So as B is gone, I'm going to have 3, 4. Then I come to the C. And of course, the C2 also has FG, right? So I'm going to have 5 and then 6. So I'm going to have D and then E. This goes away. This goes away. Then I'm going to have F and G. Can you see that? Okay, so let's look at the DFS. Of course, the DFS too, I'll have to use a different marker. So I'm going to use, let's say, a green marker. And then of course, the starting node is still A, right? Let me use B here. So this is gone. Starting with A. Then I come to the first node, which is B. Out with B. I cannot go to C. I need to finish B. So I come to D, which is number 2. Out with D. But this goes, then E also goes. It's gonna be 3. Then when I'm done with the completing exhaustion of B, I cannot come to C, just second friend of A. That becomes 4. So I'm at C. I can now go to F. Then I can now go to G. So that'll be F. And then G. Any question? Any questions so far?
Hello, sir.
Yes.
Are you to show the cancellation on the graph?
At
The queuing, the queuing
all I need from you is the output.
is the output.
Yes.
Okay. So if you can look at it and write the output, no problem.
Yes, if you can look at it and write the output, no problem. All we care about is the output. Okay.
Okay. Thank you.
Any other further question?
Hello, sir.
Yes, please go ahead.
Yeah, my question has to do with the matrix. Yeah, one with the matrix.
Okay.
Yeah.
Queuing.
This
Yes.
one.
Yes, please. So I wanted to ask, this graph you're having here is undirected, right?
Yes, this is narrated. Yeah.
Yes. So let's say we have a directed graph. But in this case, maybe the node A is directed to has two edges, one going to C and one going to B. Okay. So let's use this as an example. Let's say we have the four edges A, B, C, and D. Okay. But in this case, A goes to B and B also goes to A. Okay. And A also goes to D, and also D also goes to A. So in that case, how are we supposed to represent that using the idea of matrix or the adjacent matrix?
You mean A goes to B and B A also go to C and then C come back to A. Is that not it?
A goes to B and also B goes to A.
Yes. So if A goes to B, right? And B also comes to A, then it looks like an undirected one. Because A can be a source or origin and B can be a destination. Likewise, B can be a source or origin and A can be a destination. Because your arrow you're talking about is like this, right? Is that not it?
Yes.
Okay, so if that is the case, we can model it in both ends. So I can have my A, right, map to B, which is this case.
Yeah.
And then I can have my B map to A. In this case, here will be 1.
Wow. Okay.
Please, you understand?
Yes.
I'm sorry. So that place will be 1. I'm sorry. Yeah. Okay, there we are. Good.
So yeah, so in that scenario, it can actually be represented using a matrix.
Yes, the adjacency matrix form, you can. Okay. Any further question? All right, so if there's no further question, next week, Saturday, we agreed on next week Saturday for the IE, right? Is that what we agreed on?
Yes, please.
That's what we were told.
All right, so can you send me a reminder probably Thursday, right?
Okay, say.
Yes.
Yeah. So please, before you leave, someone was suggesting if you can kindly upload the video for the trees lecture on Sakai.
I think if the person can send me the link, Nelson or Amma, either you send me the link on WhatsApp, then I'll upload it.
Okay, say.
Who recorded it? So whoever recorded it, maybe communicate with your classroom.
Okay.
When you send me the link on WhatsApp, then I'll upload it. Okay.
Okay.
Hello, sir.
I think you don't have a slide, so I'll upload that one. Yes, go ahead.
Hello, sir.
Please, my question is,
Sir. Hello.
Yes, please, I can hear you.
How many questions?
I don't know yet. I'm here to put it together. I don't know.
I also have a question though, with regards to the exams. I want to know the slides that will be examinable, like those we are supposed to study though.
For the
Even
exam,
though, yeah, with regards to the exams.
yes, everything up to session 11.
Okay.
Okay, so
Even the I up to 11.
You?
Sir, please, will you share the slide for us? This one.
Yes, I'm doing that on Sakai right now for you guys.
Okay, sir.
But
So
sir,
that-
today you were like some of the things we will be learning them in level 200 or so. So that one won't be examinable.
And those ones, those data structures things will not be examinable.
Okay.
But
But then that's
CT one will come. But the things I wasted my time to explain will come, right?
okay.
okay.
This is
Thank
now.
you. Yeah, that's okay. Thank you.
So for now, please learn everything up to session 11. Okay.
Okay.
Thank you.
You're welcome. All right.
Tiatio, Yanyanda. Yanyanda.
All right. All the best, guys. Safe.
Thank you. Happy Easter.
All right. Many happy returns to you.
All right. Enjoy your Easter.
You too.